So today we start with next point, which is about binary operations. So you recall, for example, addition on numbers. If I consider set as all real numbers, if I take any two real numbers, so for every two real numbers a, b belongs to R. If I apply the operation, that is if I find a plus b, then you know sum of the two real numbers is always a real number, so this is in R. Similarly for multiplication, if I take operation as a multiplication on, again if I take real numbers, so for every two real numbers a, b belongs to R, if I multiply them, that is if I find a into b which is also in R. So any operation which satisfies this property or this property is called binary operation. What is the meaning of this? Pick up two members from the set, apply the operation, whether it is a multiplication or addition, the resultant member must be in the same set. Then such operation is called binary operation. So in general, there is a definition here. So an operation, so it could be anything in general. It can be multiplication, here addition, it can be subtraction, it can be division, anything. It can be union, intersection. So we in general denote by this asterisk symbol. An operation asterisk defined on a set. So here we take one set. On a set A is called binary, binary operation if you take any two members from the set. So for every a, b from the set A, now we apply this operation, that is a asterisk b, the resultant member must be in the same set. If this is true, then such operation is called binary operation. Take two members from the set, apply the operation, whatever that resultant number, that must be on the same set, then such operation is called binary operation. Now this sometimes can be written in terms of a function. So alternatively, a function, so here asterisk, how many members you are taking? 2. So a cross a, that means you have taken two members. If you apply this, then resultant member must be in a only, the image must be in a only. So a function from a cross a to a is called binary operation, binary operation. This is just alternative way of defining binary operation. What is the important thing you need to remember is this: pick up the two members from the set, apply the operation, the resultant member must be in the same set for every two members, then this asterisk is called binary operation, as I explained here. So addition is binary, multiplication is binary. So for example, if I take addition, if I take subtraction, even if I take multiplication, these three operations, if I consider on real numbers R, then they are binary operation. They are binary operation. They are binary operations. Binary operations. Why they are binary operations? I already answered for these two here. They are binary operations because you take any two numbers, for every a, b from R, you find their, for example, subtraction, which is also a real number. Find their multiplication, which is also a real number. Find their addition, which is also a real number, R. So because of this, these three operations are binary operations on R. Now, if I take here asterisk as this subtraction on a set A equals to, I'll take natural numbers. The question is this binary on this? So answer is no. Then asterisk equals to this on this set is not a binary operation, not a binary operation. What's the meaning of this? If I pick up any two members from the set, for example, because of this, suppose I've taken 1 and 2 from n, apply the subtraction 1 minus 2, which is minus 1. This is not in n. Remember, if I write 2 minus 1, then of course it is in n. But here you have an example for which the resultant member is not in the same. That's why it is not a binary. Right? If it is a binary, then for every two members, if you apply the operation, then the resultant member should be in the same set. Here you have an example. You can find many such examples for which if you apply this asterisk equals to the subtraction here, resultant member is not falling in the same set. That's why it is not a binary. You can take these also. In fact, if I take here asterisk as let's take division on a set, let's take a equals to z, for example, then it is not a binary, which is obvious. It is not a binary operation, not a binary operation. Why? Because you can find two numbers as, because of, you can take 1 and 2, both are in z, for example here, but if you find 1 by 2 division, 1 by 2, which is not in z, that's not in z. So because of this one example, you can say that it is not a binary. If it is a binary, then for every two members the division must be in z, but here it is not. Therefore it is not a binary operation. And so on. You can find many such examples. Now we move ahead. Next one is about commutative. You know such properties: commutative and associative operations. Associative operation. So we start with a binary operation, remember. So let asterisk be binary operation on a set A. Binary operation on a set A is called first one, that's commutative, is called commutative if this is true. If I find A asterisk B, if I find B asterisk A, both must be same for every member of the set. Remember, what's the meaning of this? Order is not important, whether you find A plus B or B plus A into B or B into A. If this order is not important, the way the operation is applied, whether it is for A asterisk B or B asterisk A, both are equal, then it's called commutative operation. Then asterisk is called associative, which also you know. Associative if A asterisk B, will find this first, asterisk C. On the other side we find B asterisk C first, asterisk A. Members are taken in this way. Here A asterisk B first and then C. Here B asterisk C first and then this with this. These two are always equal for every three members of the set. Then this operation is called associative. For associativity you require three members. Commutativity you require two members. You know simple examples. For example, addition and multiplication are both commutative and associative, are both commutative and associative on, you can write all real numbers on R. Because of this, you know this A plus B is always B plus A. That's very basic. A into B is always B into A, you know this. So because of these two things, you can say that addition and multiplication are commutative. These also, you know, if I find A plus B plus C, if I find A plus B plus C, Similarly, if I find A into B into C and A into B into C, these two are always equal. This is very basic since your primary schooling, A plus B is always B plus A into B is always B into A for any two real numbers, remember. Similarly, these and these. Therefore, addition and multiplication are both commutative and associative. Next, if you recall, on sets, if you consider union and intersection, these two operations. A union B for any two sets is always equals to B union A. A intersection B is always equals to B intersection A, if you remember. That means these both operations are commutative. Just recall from 11th standard, commutative operations. Even if you recall for three sets, A union B union C, A union B union C, these two are always equal. A intersection B intersection C is always equals to A intersection B intersection C. That means these both operations are associative. This is always true. One more, if you remember, on matrices, you already studied. If I take asterisk as, for example, multiplication, then we know this. We know that A into B need not be same as B into A for two matrices A and B. It means multiplication is non-commutative. You know this. I'm just reminding you. But they are associative. But you know this, for three matrices A, B and C, if I find this and if I find B into C into A, these two are always equal. That means this matrix multiplication is associative. This, matrix multiplication is non-commutative. But for three matrices, if you find A into B into C and B into C into A, these two are always equal. So matrix multiplication is associative. Fourth, if you remember, on functions, just previous topic, you take asterisk as composition, composition operation. So for functions f and g, in general, if you find f of g and if you find g of, these two need not be equal. So you can say that composition is non-commutative. Composition of functions is non-commutative. But if you go for three functions, f, o, g, o, h, h is the third function, and if you find g, o, h, o, f, you are just changing the bracket here. These two are always equal. This was stated as a standard result, if you remember. So composition is associative. This for standard functions is associative. If you find this and these two are always equal. Composition on functions is always associative. Composition on functions is non-commutative. Next is about identity or unit element. So we start with a binary operation. Let asterisk be this be a binary operation on a set A. So you started with a binary operation on set A, and an element E, small e, in A is called identity. If this is true. If this element is applied for every member of the set A asterisk E, and even if the reverse is done, these two must be equal. and these elements should not have effect on this, that is, the answer should be A only for every A in A. What it says, this element has no effect with respect to this operation. So for every member of the set A asterisk E and E asterisk A, answer must be A. Then this is called identity. Remember, identity is like whenever identity exists, then it is unique. E is unique, means exactly one whenever it exists. Whenever it exists. If it has exists, then it must be exactly one, that is unique. You cannot have two different identities, remember. It has to be one and only one. Unique means exactly one. Recall, for example, on R, on real numbers with asterisk as addition. For every real number, if I find A plus 0, if I find 0 plus A, then answer will be always A for every real number A. So this become identity. So E equals to 0 here. So with respect to addition on real numbers, identity is 0. You go back to multiplication on real numbers. If I take asterisk as multiplication, there's all these things for every real number A into 1, 1 into A, answer is always A. So with multiplication, 1 has no effect on every member for every A belongs to R. So you can say that this 1 becomes identity with respect to multiplication. So A equals to 1. This identity, remember, this identity with multiplication. This is identity with respect to addition. Even on matrices, on matrices also, on matrices, A into In. So here asterisk is multiplication. In into A equals to A, if you remember this. Then here E is identity matrix, this. In, that's identity matrix. Identity matrix here. So E becomes identity here. If you remember, if it is I2, it is 1 0 0 1, if you recall. Identity matrix into any matrix gives you that matrix always. Even order is also not important. These also from matrices. So for addition, identity is 0. For multiplication, identity is 1. On matrices, identity is identity matrix. On sets, let's take asterisk as union operation. This is union operation. This is a binary operation, union. For any set A union one set equals to that set union A, then answer must be A. So what do you think here? Which set you can put here? A union one set equals to the same set union A, then the answer must be A for every set A. So obviously, if you recall union operation, this is nothing but null set phi. So here identity become phi. So this is identity element. So what I'm trying to tell you is identity can be set. So on union operation, identity is phi. If you go back to previous example, their identity was matrix and so on. Even on functions also, on functions, if you remember, in the previous session only we did this. For any function f, composition equals to f again. If I reverse this, composition of f is again f. So here answer is identity function, if you remember. Identity function. Here I is identity function. So in this case, our E is I, that is identity function, it. We have stated as the standard result. Function composition with identity function gives you the function itself. If you reverse again, you will get the f. So here identity is identity function, here identity is a set. Okay, I hope this is clear to you. Now we go to next, that is inverse element. Inverse element. So we start with a binary operation and identity element. Let asterisk be a binary operation. Binary operation on a set A with identity equals to small e. With identity equals to a. So whenever you find inverse, you require identity, remember. Let asterisk be a binary operation with identity element this e. So I'll write an element, say B is called inverse of A, an element A. So B is said to be inverse of A if this is true. You apply asterisk operation between these two. Find A asterisk B, find B asterisk A. Both should be equal and answer should be identity. A asterisk B and B asterisk A. One element is said to be inverse of the other one. If you apply the operation between those two members, the answer should be identity. So here B is said to be inverse of A. So it is denoted by this symbol here, denoted by B equals to, B is inverse of A. So we write A raised to minus 1. This is a symbol. You are very much familiar with this symbol. This is read as inverse of A. It does not mean that it is 1 upon A, remember. This never mean by A inverse. This is the inverse of A means this. That is, you can say that A asterisk inverse of A, that is A raised to minus 1. If you do reverse, A inverse asterisk A, the answer must be identity. So what this result says, one element is said to be inverse of the other one. One element is said to be inverse of the other element if their asterisk must be identity element, you know, from matrices and functions. For example, you take on real numbers on R, asterisk as addition. So we have, you know, E equals to 0. So therefore you can write A plus, you find one member here, that member plus A. Why I'm taking plus? Because my operation is plus A, then answer must be identity, which is 0. Then this element is said to be inverse of this. So you know here which appropriate element should be placed, here and here, that is minus of A. So here you can say that inverse of A is minus A. You know that this is sometimes called additive inverse. For example, what is the inverse of 2? That is minus 2, because 2 plus minus 2 is 0. If I do reverse, minus 2 plus 2, which is also 0. So you can say that inverse of 2 here is minus 2, remember. So 2 raised to minus 1 does not mean 1 upon 2, remember. If I take this here, for example, 4 by 3 plus minus 4 by 3, you know 0. Even if you do reverse, minus 4 by 3 plus 4 by 3, answer is here identity. 0 means identity here. So you can say that inverse of 4 by 3 is again 4 by 3. Sorry, minus 4 by 3. That way. Now, if I take on all real numbers other than 0, 0 I'm not going to take here, an asterisk as multiplication operation, then we have, you know, we have E equals to 1 identity. We did it, you know it. Identity is 1 with respect to multiplication. Now you recall, you know this, any member, any real number other than 0 into, you find one member, that member into A, your answer must be E. E means here 1. So which appropriate member should be placed here? It is, you know, reciprocal, 1 upon A, 1 upon A. So you can say that here inverse of A is 1 upon A. This is with respect to which operation? Multiplication. Remember, this was with respect to which operation? Addition. That's the difference. Keep operation in your mind. Here operation is multiplication. Here operation is addition, remember. So this is true for every real number R other than 0, remember. 0 has no inverse, you know it. So here if I write inverse of 2, it is obviously reciprocal, which is 1 upon 2. If I write inverse of 3, it is 1 upon 3. Why? Because here product of 3 and 1 upon 3 is 1. That's why. Why inverse of 2 is 1 upon 2? Because the product of these 2, that is 2 into 1 upon 2. If I do reverse 1 by 2 into 2, it is identity, which is 1. Therefore, this become inverse of this. Same way here, 3 into 1 upon 3. If I do reverse 1 upon 3 into 3, answer is identity, which is 1. Therefore, this become inverse of 3, and symbolically we write raised to minus 1. So this is read as inverse of 3 is 1 upon 3. On matrices, we did it. If you recall, A into 1 matrix equals to that matrix into A. It means asterisk is multiplication, remember here, equals to IN, that is identity matrix. This is E, identity. So you know here that A inverse, and there is a prepared formula to find the inverse. You know it. Even on functions also we did it. On functions, if I take asterisk as composition here, then FO, you find a function here, then that function which we called F inverse, OF, answer must be I, that is identity function, if you remember. So this become inverse of F, this become inverse of F. And you know very well here, inverse doesn't mean 1 upon F. This is the inverse of F, means their composition is equals to identity. This is the inverse of this matrix, means this product equals to identity. That's the concept. Okay. Now, if I take a simple example here, for example, let me take one example here. Binary operation. You are given the binary operation asterisk on Q. Q means set of rational numbers, you know, as A asterisk B equals to AB by 4. This is given to you. This is given to you. For example, if I understand here, what is 1 asterisk 2? That is 1 into 2 by 4, which is 1 by 2. For example, what is 3 asterisk 4? That is 3 into 4 by 4. So answer will be 3, that way. This is the meaning of this operation. A asterisk B means A into B by 4. Now, it's already binary operation. So first I want to check the commutative property. So clearly, if you are given A asterisk B, which is AB by 4, and here if you find B asterisk A, which is BA by 4, now obviously AB by 4 and BA by 4 both are equal. So you can say that A asterisk B equals to B asterisk A for every AB in a set Q. So you can say that asterisk is here commutative operation. This is a commutative. You find A asterisk B, you find B asterisk A, then both are equal, remember here. Because AB and BA both are always same, because this is just a standard multiplication. Like this is just for your reference. You find 2 star 3, which is 2 into 3 by 4, which is 6 by 4, that is 3 by 2. If you find 3 into 2, 3 star 2, which is 3 into 2 by 4, which is also 3 by 2. This is just for your information. It's quite obvious from this. So it's binary operation. It's a commutative operation. Binary is already given to you. So next is associative property. So I'll find A asterisk B asterisk C first. What is A asterisk B? We apply first row bracket, that is AB by 4 asterisk C as it is. This is given to you, remember, in the question itself. Now you imagine this is like A and this is like B and apply the star. Now what is the definition of A star B? That is A into B by 4. This is given to you. So A means AB by 4 into B here, that is C, the whole by 4. So you'll get the ABC by 16. I repeat this. See, first you come to this. What is the asterisk B? AB by 4 asterisk C as it is. Now you consider this like A and this is like B. Now what is the rule for A asterisk B? First into second by 4. So first into second by 4. So you'll get this. And if I go other way around, that is if I find A asterisk B asterisk C, so I'll keep A asterisk as it is. What is B asterisk C? Again go for the rule. First into second by 4. So you'll get the BC by 4. First into second by 4. Now this is A, this is B. Again you apply the same operation. What's the rule again? If you have A asterisk B, then first into second by 4. This is given to you. So first into second, that is BC by 4, the whole by 4. So finally you will get ABC by 16. So you notice that these two are equal. So therefore for every 3 members, A asterisk B asterisk C is same as this. For every 3 members, remember, there is nothing special about ABC here. So you can say that asterisk is associative here. Asterisk is associative. Now next important property, that is about identity element. Identity element. This is very important part to get the identity element. So what we do in such questions, this is very commonly used standard technique you use in every question. So let identity equals to E. Now if E is identity, you know A asterisk E is always A. Even this is also true. E asterisk A is also A. You recall the definition. A asterisk E, E asterisk A, both are A, but I'm using just this one only. You can use these also. Any one of these two can be used. This is a definition, remember. Therefore, you have this by definition. We want E. That's the question. Question is get E. Now apply definition of asterisk. What's the definition of asterisk? First into second by 4. So first into second by 4 equals to A. Our question is find E. So A will get cancelled. So E is 4. So here identity is 4, remember. So in this case identity is 4. If you want to see, for example, you find 3 star 4, your answer has to be 3, remember, because this 4 being identity should not have any effect. Why? Because you recall the definition, 3 into 4 by 4. So 4 will get cancelled, you will get 3, same element. So this has to be identity. So here identity is 4. Now inverse element. So for given an element A, we find its inverse. We find A inverse. This is a question. Now this is again very standard technique. Now if this is the inverse of this, you know A asterisk A inverse should be identity. You can use these also. A inverse asterisk A equals to identity. Any one of these two can be used, remember. I'm using this. We want this. This is by definition. If this is the inverse of this element A, then the asterisk must be identity. Now what is A asterisk B? You recall. A asterisk B is AB by 4. This is given to you in the question. So here what you will get, A into A inverse by 4 equals to E, but E we did, it is 4. To get the inverse you must have identity, which we did in the previous part. E is 4. A asterisk B is AB by 4, so A into A inverse by 4. We are interested to find A inverse, so A inverse will be 4 into 4, 16, and A will come down. So you have this is the formula for inverse. So now suppose if I want the inverse of 3, for example, then 16 by 3. This is the formula. If I want the inverse of 4, then it would be 16 by 4. It would be 4. What's the meaning of inverse of 4 is 4? It means if I apply asterisk between these two, 4 asterisk 4, you can check that your answer has to be E. You can verify. What's the meaning of inverse of 3 is 16 by 3? That is, if I find 3 asterisk 16 by 3, you can verify that your answer has to be identity. What is the inverse of, for example, there's 1, 2. If I take, for example, let's take inverse of 2. So it would be by this formula, 16 by 2. So it is 8. Now again, just I'm emphasizing, inverse of 2 is 8. It means if I apply asterisk between these two, that is if I find 2 asterisk 8, your answer has to be identity. You can verify. So this is about inverse. This is very commonly used standard technique to get the inverse, remember.